Okay, so in this video, we're going to look at another application of the idea of linearization, and it is the use of what is commonly known as Newton's method. Now, recall that Newton's method is a way to approximate a zero of a function. But what we're going to do is kind of start with a problem that doesn't even appear to have a function, create the function that is needed, and then apply Newton's method. So the goal here is to approximate. So let me get this here. To approximate the cubed root of 50 to within, actually we'll say, instead of to within, we'll say using 3 steps of Newton's method with initial estimate of x equals 3.5. Okay, so that's our goal here, to approximate the cubed root of 50. Now, the problem with this at the moment is, recall that Newton's method, I want you to remember what it basically is doing. So let's suppose that I have a graph of a function, and let's just say that it looks something like this, and it crossed here at whatever that point is. And so what Newton's method is going to do is you take an initial guess, and so maybe my initial guess is, this value right here. I come up to the function there, and I draw a tangent line to that function right there. And then what I do is I say, okay, I zoom in on this right here. So this might be something like, if I zoom in on that, it'll look something like this, where that crosses and then this crosses. And what I do is I use where the tangent line crossed as my new estimate. And in general, you will note that it will be closer than the first estimate. And then you do the same process over. So that's my new estimate. I come here and I do a tangent line, and I keep doing this iterative process, getting closer and closer until you get as close as you want to. Okay, so what we need is a function, because we're going to take the derivative of that function. Well, so I need to somehow turn this into a function. So I need x equal the cubed root of 50 to be my root, or my zero. Well, so now if I solve that, I'm going to cube both sides, so I would have x cubed equals 50, and then I would have x cubed minus 50 equals 0. And notice that the cubed root of 50 is a solution to this. So this will be my function here, f of x equals x cubed minus 50. And now what we're going to do is we're going to use the Newton's method. And remember that the formula is, and I want to talk a little bit about where this comes from, but the formula is basically this, that the next term is equal to the previous term minus the function at the previous term, I should say n there, sorry, divided by the derivative at the previous term. Now, where does this come from? Well, this comes from this idea right here, where we used the tangent line and we found where it hit 0. So think about this. This is the tangent line, which we could think of as being y minus the function value. So that's going to be x sub n. That's y minus y y1 minus y2 there equals the derivative value. So I'm going to do that in red. X sub n times x minus your x sub n. Okay, so notice that when we do that, I'm going to bring that down here. So I get y minus my function value equal to my slope, which is the derivative, times x minus my x value. Now, remember what I'm solving for is I'm trying to solve for, I want y to equal 0 because we want to know where does it cross the x-axis. So I'm going to put a 0 there. And then I want I want to solve for the x value. So what I'm going to be solving for is the x value. So notice that I've got this negative here. I'm going to divide by the first step would be divide by this. So what I would get is negative f of x sub n divided by the derivative at x sub n. And this will equal x minus x sub n. That should be x sub n, not x sub 1. And then I will add this over here, and there is my formula. Okay, so this is basically saying that the root of the tangent line is found by doing that, and that gives me my next value. Okay, so keep in mind that our function is f of x equals x cubed minus 50, and my first guess is 3.5. So therefore, my second x value would be equal to my first one, 3.5, minus my function at 3.5 over my derivative at 3.5. Now, before we go any further, let's look at the graph here. So this is the function, and if we were able to kind of zoom in on this, you can kind of see that. So this is 3.25, 3.5, 3.75. So the root appears to be something in the neighborhood a little bit less than 3.75, so something really close to 3.7-ish, okay, is what we're thinking that it's going to be close to. Now, what we've done is, or what we're about to do, this was my initial guess down here. So right here is my initial guess of 3.5, and I create the tangent line at that value, and I'm looking for where does this tangent line intersect the curve. Now, notice what happens when I do that. So when I do that, I'm going to wind up with this value right here, and then I'm going to use it as my next guess, and it's going to come up here. Now notice when I do that the tangent line there will intersect much closer, right? The tangent line right there will intersect much closer, and that'll be my next guess. And then the tangent line there would be much closer and closer and closer. And so you can see that if you have a good first guess, which ours wasn't bad, that it's not going to take very long to get a really accurate approximation. Okay, so if we do this here, this turns out to be, now we're probably going to have to do some rounding here, but we're going to get 3.5 minus, now this is going to be 3.5 cubed minus 50 over, now let's think about the derivative real quickly. And I didn't write that down, but I will here. The derivative of this, f prime of x, is equal to 3x squared. So then all I have to do here is say 3 times 3.5 squared. Okay, and so that will be my next value. Now, just to do this, let's come to Desmos, and we'll have Desmos do that for us. So we have 3.5 minus, and then we will have 3.5 cubed minus 50, all divided by 3 times 3.5 squared. And we get 3.69, we'll say 39. 3.6939. So this is approximately, so x of 2, we'll write it here, x of 2 is approximately 3.6939. Now we would do this again and we would look for x of 3. So x of 3 would be 3.6939 minus f of 3.6939 divided by f prime of 3.6939. And you can see that, you know, it's just going to get closer and closer. So let's do this one on Desmos. So we're just going to change all these to 3.6939 and then 6939 and then and notice we get 3.6841 ish. So 3.684. Now we're going to stop after this, and let's just check it here. Let's just kind of see if I cube this. So this is what we want to know. If I take this 3.6841 and I cube it, what does that give me? It should give me something really close to 50. So let's see here. 3.6841 raised to the third power is 50.002. So notice if I had done, if you look up here, right, and this one is 684,057. So if I'd have done that instead, 684,057.8, notice that it's getting closer and closer and closer. And then we could have said 4. And notice it's getting closer and closer. And you can just keep doing this as long as you need to get as close as you need to the actual answer.